Hello, welcome to my session for today. I'm going to take a couple of minutes to guide you through a step-by-step process on how to implement a rich linear regression model on a particular data set, and also how to perform cross-validation, apply a cross-validated grid search to tune also the value of the regularization strength. So this is a very interesting topic for me because I think as a data scientist, we need to understand how to increase the validation score, and hypertuning the parameters is one of the main things to do on a particular data set once everything is in place, once the machine learning model has been already implemented. So by saying that, I'm going to share my screen, and please don't hesitate to follow along. I have already a couple of lines of code right here so that we can have everything prepared to start. So I'm using Jupyter Notebook. In case you want to use it in your local host, you can download the Anaconda distribution. I just put a link here that you can actually access. And so I went on and imported the libraries that I needed for today. So we are going to use a dataset. This is going to be a data frame type, and we are going to use sklearn, which is the to-go-to machine learning library of Python. And so what we are going to do today is actually to use a data set already made available by people to us. And this is called California Housing Dataset. It is a very well-known data set, but it's a great one to work with when you want to apply some sort of supervised machine learning algorithms of regression type. Why regression? Because actually we are going to try to predict the price of housing. And so the price being a numeric variable, we are eager to implement some sort of regression and not classification, which would be applied on target variables of categorical type in that particular case. And so I'm going to upload some, import some modules that are going to make our lives easier in terms of automatizing this entire process. So we are going to use a module called pipeline and compose. I'm going to explain to you what this is about. And of course, we are going to use some modules that are going to perform some type of pre-processing steps so that we make sure that the data set that we take into consideration is going to be clean and preprocessed for our machine learning algorithm. And so what I also did here was to download the data into a pandas data frame. So actually this data frame I'm calling a data set, and I just went to data sets that fetch California housing. I copied and pasted the indication over there. So here I just have a link. So this is the sklearn that datasets fetch California housing. I just copied this particular code and transformed it into a data frame. And so in this code, it states the fact that there are two types of information. One is the target itself, which I'm calling price, and the other one is composed by columns that are actually the feature names or the explanatory variables. And so if I want to see a bit more about information about this, what I can do is just make sure that the price is added also to the data set. And if I am pressing Shift Enter, I'm going to take a look at the first rows by using the head function, the first rows that show me what the data is about. So it's a nice data set to work with. You have a lot of numeric variables. You have 2, 6, 7, 8 explanatory variables, and the price being the target. So you can take a look at it if you want to. We can also print the description of the uploaded data set, and this is done by writing print function, and inside we have the data that description. This is the way in which we can visualize the data set. and we have additional information over here. We have around 20,000 rows or observations or individuals represented by a particular house here. This is called instance, 8 numerical variable, and 1 target. The target actually is the amount of money estimated for which a house can be sold. So the target variable is the median house value for California districts expressed in hundreds of thousands of dollars. So if we take a look just above here, we see 4.5 for the first row. That would be $450,000 for the first observation or for the first house. Of course, there is a bit of metadata over here, so you also have information about the attributes or the columns that are explanatory to this price, and you can go ahead and read a bit more about it if you are interested. But what I want to do right now, let's say that I am actually a user of a data set and I did not actually have the possibility of searching information in a particular application. This is what AI platforms could do once the entire machine learning pipeline would be implemented. But let's say I would like to just filter my 20,000 something values based on particular conditions. Okay, so let's think here that we want to we would normally want to clean this data set. Okay, we are not going to do that because it's not the purpose of today's exercise, but this is what we call a bit of data cleaning, or maybe removing some outliers. And in this case, let's say that we are removing outliers by implementing some conditions on the data itself. So what I like to do actually, and of course in Python you have so many ways through which you can clean your data. This is just one of them. I love implementing a mask. So this mask is going to actually be a new variable that is stored in the temporary memory of Jupyter Notebook here. And so what I'm going to do right now, I'm going to open the parentheses and I'm going to say like that: I would like that the data set average rooms to be less than 10. So the column for average rooms in this case, I would love to have it less than 10. Okay, so what I'm going to do right now is to write the data set and open the parentheses for average rooms. I need to make sure that I have these values in quotation marks, and I'm going to close this particular parenthesis. So this value is smaller than 10. Okay, so this is my first condition, exactly what the assignment asked. We want to have an average number of rooms per household less than 10. And in addition to that, we would actually want to have, so I'm going to copy paste this because it's almost the same thing. Average number of bedrooms per household less than 10. So average bedrooms here. Also, I would like to add an additional criteria, average number of household members. So average occupants less than 10. And the last criteria would be that my data set, the price of my house price would be less than $500,000. So let's say I want to create this data set over here, and so out of the 20,000 something rows, I will have less than that just because I applied this criteria. And now I will apply this data set to the this mask to the data set. So I'm going to write data set equals data set. So I'm going to override the previous data set information with the new one. So I'm going to create this, use this lock so that I make sure that I am locking the position. So actually I'm going to write mask, comma, 2 points. So what this is going to actually do is to to implement this criteria. So this is just a filter, like a where from SQL, if you will. So from the previous data set, I'm applying all this criteria and I'm saying, well, please keep only on the rows positions where the information fulfills this criteria. So I'm going to Control Shift, and of course I have an error, which can happen pretty frequently. Maybe I did not write something well, so allow me just to make sure that I didn't misspell something somewhere. So I'm going to put this correct form over here, and yeah, I might have missed something that gave me an error. This is the correct format, and now I have less information than before. And so what I can do right now is to follow the assignment. And so the next step for me would be to separate the target variable y from the features x. And this is something very easy to do. What you need to do is to identify already the target variable. In our case, it is the price, target variable being the y. So I'm going to write target underscore variable equals price. And so what I'm going to do right now is to say that I have an X data set and a Y data set. And so the X is equal to the previous data set, where we are going to drop the target variable. So what we are going to do is writing data set that drop. So drop being the function where we are taking out the target variable. So I'm just going to code it here. And I'm saying that this drop actually applies to the axis equals 1, which I mean by taking out this value from the columns dimension and not from the rows dimension, the rows dimensions being the axis equals 0. So here I'm going to write axis equals 1, okay? And so this is exactly the same thing. Here I'm going to have X without the price. And here, if I'm going to copy the same thing, so I'm going to write in Y, I just want to have the price. So once again, I can use a lot of methods. The one that I prefer right now is this one, dataset.lock, and I just copied, pasted the thing from above. So I'm saying take all the rows, please, and keep just the target variable. And so this is what this lock functions does right now. Of course, I need to pay attention to the syntax. Sometimes I'm making some mistakes, but I can just shift enter. And if I'm adding a new row and I'm visualizing the X, this is actually the same data set as before, filtered and without the price. Whereas if I am writing the Y right here, I'm going to have just the column price itself. So that's great. It means that a half of the job has been already done, because as you know, more than 80% of the time you might spend on cleaning the data, preprocessing the data, and just understanding how to upload it, how to collect the data, and how to work with it. Let's consider that this part was done. The aim of the exercise is actually to focus on the next steps. And the next steps is just to go and see further on what's happening. So let's check the column types. I'm going to focus myself on the X.info. And so I just want to see actually what my column types are in the X data frame. So here I'm just writing X.info, which is the function that is going to show to me what is the type of this information. And I want this because I want to be able to understand what types are my column. Let's say we don't have just a couple of them, like 8. We might have hundreds and hundreds. And so the next step that we want to do right now is to automatically detect names of numeric and categorical columns in a particular data set, to make sure that we don't write them by hand. And I would actually advise in creating automatically code that detects automatically these types of behaviors, just to make your life easier. So the next step would be, okay, I have my X. It has just float types in it. Maybe there are others that have integers, who knows. My aim is actually right now to be able to detect particular categories in my columns and to be able to split them. Because the next step that I want to apply is actually to make sure that when I'm applying some pre-processing steps, well, I'm doing them according, like in relation to the type of each column in part. So for example, one-hot encoding is something that we would apply on categorical variable only, and we would receive an error if we would apply it in bulk with other numeric variables. And so that's my reason here. And let me just do that. We are going to create a list, a blank list for numeric features. So numeric underscore features equals, and I'm going to create a list just like that, and it will be categorical underscore features list blank, just like that. So what I'm going to do right now, I'm going to make use of one of the pandas data frame iter items, it's called, which iterates over the data frame columns, returning a sort of a tuple with the column name and the content as a series. Why do I want to do that? Well, actually, because I am going to say I want to create an entity that has the names of only numerical features and another entity that has the names of only categorical features. So what I'm going to do right now is write for I and T in x.b types. And this is something, if you remember, that we just took a look at with the x.info. So I'm saying like the types are over this, I'm going to apply an iter items function. And so what I'm going to say is that if the column is of float type, which in our case it is, in string of t, okay, or if the column is of integer type in string of t, well, what I want you to do is actually append these values, append these values to the numeric features. So here I have numeric features. So if the category, if the column is of numerical type, then add it please in the numeric features list, append. And if not, so else, well, add it in the categorical features list. So this way we are going to actually have two lists with names of numeric and categorical type. And if I am to ask you, well, is there any information in the categorical type? I'm sure that you would all say no, because actually we don't have any category by the output that we just saw before. So I'm going to just print the numeric features here. And so this is the contents of the numeric features. And if I were to actually print the categorical features just to look at them, you would see that there is nothing inside. So we wanted to do that because we wanted to take into consideration the possibility of putting a machine learning model in production and of rendering it adaptable to any new sort of data that might come. And so you always need to think big at a big scale, because let's say we would add additional columns or we would add additional rows. Well, actually my machine learning models and my algorithm needs to take into consideration this type of automatization. I love it. It's something that I would definitely want to do if I were in your place. And now I'm going to divide the data set, train set and test set. And we are going to do that because we want to train our machine learning model. And here just above, I copy pasted a link that I find very, very useful to explain when people ask me, well, why do we split in X train and X test, Y train and Y test my data set? And just allow me to give you a sort of a 1-minute description on it. Well, we would upload the full data set, and this is the look of it. And we are going to split this data set in features and targets. So we want always in machine learning to predict the target in case of supervised machine learning models. And we are going to use all the columns that are explaining the price in this case to do that. So that's why we just created here the X and Y variables data sets separately. So this is what we did. And now we want to divide this data set train set and into train set and test set. So this is what it will look like. And we are doing that because we are saying, well, we are going to randomly take rows from my data set and make sure that, let's say, 80% of it is part of the X train and Y train. And so what we are going to do is we are going to train our machine learning model and predict what the price is, knowing what the price already was. So actually we are going to have the price, and we are creating coefficients that are going to be adapted during this process of training. And so what we are going next to do when actually implementing this machine learning on the test would be to take these coefficients and apply it to a new data set. So we are going to take the coefficients and apply the coefficients to the new data set to see if actually we were able to see the patterns both in train and test. And so we are using the training data sets for training purposes. And so once we have the machine learning pattern out of it, through having the values of the coefficients of this particular machine learning pattern, we are going to take these coefficients and apply them in the testing part. And so this is how, at the end of this entire process, we are going to have 2 scores, one for training and one for testing. And the aim for us would be, first of all, to have this score as high as possible, as close to 100 as possible, so that we know that we do not have a lot of mistakes in our prediction. And of course, the idea would be to have the score for training and testing as close as possible as well, so that we don't have over or under sampling. And so let me just continue here. We are now going to divide the data set. And so I just went online and I copy-pasted just the line that explains, that creates this particular code. And I just clicked on Shift-Enter. And so now we are going to do the pre-processing steps. So in the pre-processing steps, this is how it looks like. And so I just showed here I have 2 different cells to show you how to take a look at an image both ways. So we are going to apply a sort of a pipeline on our data set so that we make sure that we also automatize the preprocessing steps. So we have original data and we have automatically identified numeric and categorical data. And now we are going to apply something called column transformer so that we apply different types of transforming and preprocessing steps on these particular columns. And so you would have here in column transformer, you would have scaling applied to all numeric values in this case, and one hot encoding to all categorical values. So let's take a look and see what does it actually look like. So we are thinking in terms of numeric transformers and in terms of categorical transformers. So here I'm going to create a new variable called numeric underscore transformer. And so I'm going to use a function called pipeline, and this pipeline is going to have some particular steps for the numeric values. And so these particular steps are going to be the imputer. So we are going to consider that if there are new observations with missing values, we are going to impute them, let's say, with the mean. And so this is actually imputer. This is actually a function that we are going to have right now. So I'm going to actually open here a new parenthesis, and I'm going to use simple imputer. So this is a function that we uploaded just at the beginning, strategy equals mean. So this means that for all the numeric features that we are going to have, we are going to replace all the missing values by the column's particular mean. And we are also going to scale, apply standard scalars, so actually to normalize these columns, and this is something that we would love to do in case the unity measures are very, very different. So I would like to apply a scalar. And of course, in the specialty literature, there's a lot of discussion on when to apply the imputer, what type of imputer to apply, when to apply the standardization or normalization, and how to do that. But standard. So just follow with me, scalar, and let's actually close the parentheses, and I hope I didn't actually created any problem here. Yeah, that's great. So that's what I call creating a pipeline for the numeric features. I'm copying, pasting this, and I'm going to do the same for the categorical transformer. So here I'm going to change the name, categorical transformer. Of course, if you were here to ask me questions, I would have mostly loved, just because it's easier to have someone to speak to directly and explain this concept. So here, let's say categorical transformer. I'm going to apply just one step, and I'm going to erase this part over here. And so the step that we are going to apply is actually called one hot encoder. So this is just one step. It is called encoder, and we are going to apply one hot encoder. You might ask me, well, Andrea, how do you know all these things? Well, actually, I searched them in advance, okay? So as the developers are creating their own codes that you can copy paste, well, actually you need to respect their rules and the syntax, and so this would be something that you would do also in advance. Drop equals first. Okay, so here I am saying, and then I'm going to close to rewrite this one. So here I am saying for any categorical feature, we don't have any right now, but let's say we would have, please apply a one hot encoder pre-process step so that we are able to transform all the categorical values within the categorical column in numeric values, so that our machine learning algorithm will have an easier time to work with. Okay, and so now I'm going to, of course, have a problem. I forgot here to add a comma. Okay, and so we created the pipeline, and what we are going to do right now is to take the numeric and the categorical transformer and actually apply them to the numeric and categorical features that we created just before, right here. Okay, so let's do that together. I'm going to just say like that. Well, this is my preprocessor step, preprocessor equals column transformer, and I'm opening the parentheses, and here inside I have my transformers, and I have two transformers for numerical and categorical. So transformers, these are the attributes inside. So as we have attributes for steps in pipeline, this is exactly the same thing that we also have for transformers. So inside I'm going to have numeric transformer, comma, numeric feature. Numeric feature. So I am just mentioning the fact that I am going to apply these preprocessing steps for the numerical transformer to the columns in the numeric features. This is what I'm going to do. Yeah. And for categorical, I will have exactly the same thing. So let me just copy paste this and just change the naming. Oops. So for categorical, I'm going to write categorical. Okay. Categorical and numeric. Categorical feature. Okay. So this is, I think, features. Let me see. How did I write them? Features. Okay. So pay attention to the syntax and the naming convention that you used, because this might give you errors such as here. Column transformer. Okay. Numeric transformer. I forgot an S right here. Yeah. And categorical transformer. This is the demo effect. Okay, so this is my preprocessor. And now what I'm going to say is that I want to apply these preprocessing steps on the train set as well as on the test set. So all I need to do right now is to take my x underscore train, x underscore train equal to the preprocessor steps, and I'm going to put a dot right now and do a fit underscore transform of my x train. Okay, so I'm erasing the previous information from the x train transform, and I am actually applying these preprocessor steps over it. And I'm going to do the same for the X test. So just copy paste it. Of course, we do not need to do this for the Y, because the Y is just a numerical column that is actually our target. So test, X test, X, and here we are going to have X test. But in this case, just pay attention. We are fitting and transforming the train, but we are just transforming the test. We do not need to fit once again, because this is what we did here in the first step when we actually saw the patterns in the train and learned from these patterns. And now we apply these patterns in the test. So let's apply the preprocessing steps on the test set. Nice, congrats. So the job is almost done. What we need to do right now is actually perform some cross-validation on a machine learning model called Ridge. So just to give you a bit of context here, the regularization is a principle widely used in statistics, okay? And machine learning, so statistics and machine learning. And this allows us to constrain models and to adopt certain behaviors. So in this case, with the ridge regression and regularization in any case, it allows us to reduce the importance of variables or remove explanatory variables that do not provide relevant information for the model. And this is a case where we have thousands, let's say thousands of columns. For demo purposes, I took a very simple and short data set, but normally in real world situation, you might have thousands of columns. How are you able to see what columns are useful for you to keep or not? And so this is what the ridge models actually do. It introduces the notion of penalty. And so ridge regression is exactly the same thing as linear regression, but we would have a cost function that introduces the notion of penalty. And this modification is done in order to control the trade-off between the bias and variance. And this implies that any variation in the parameters is going to be observed and diminished in the case in which the coefficients of the functions are not very of the columns are not very powerful. So we would have this penalty called lambda, which actually in parameters in Python they are called alpha, and the ridge model behaves as follows. Lambda is 0. It means that the ridge regression is exactly a normal linear regression, okay? And when lambda increases, actually the variance decreases, and it means that we would increase the coefficients of lambda. Actually, it means that we would diminish the importance of particular columns that are not very strong as feature significance. And so this is just yet another model that I find very, very interesting. We can talk hours and hours about it. But as for the moment, I just want to create it. So let's write regressor equals ridge. So this is actually the function that is going to be applied to the train X and Y. And we are going to perform just a simple cross-validation. So we are going to create a scores equal cross val score. And so here we are going to train the regressor. So this is how I'm writing it, regressor. So we are going to train the regressor on X train. Okay, so we are training this right now in folds of 10. So we are going to, this is yet another interesting subject, cross-validation being, well, we are going to apply a machine learning algorithm on a particular train data set, and then we are going to randomize the observations from this data set so that we expand our possibility of having multiple variations of the data set, which might give us some indication on the median value of the score that we are going to have. So actually it talks a bit about the central limit theorem that says that the more observations you have and the more you shuffle your data, well, the score is going to be closer and closer to the population mean. And this is what we are trying to do right now, create like 10 different data sets. And so here I'm going just to take the mean of all the scores that have been created in these 10 iterations. So scores that mean. That's all. And this is going to indicate to us what the average score of the ridge regression in general is. And here it is. If I were to increase or decrease the number of cross-validation folds, well, actually, I would have maybe something similar to this particular value. We can change it to 5 or to 10. It depends of our computing power and how much and how big the data set it is. And so this is just a simple cross-validation, but actually we can go further on and implement this idea of ridge with changing the parameter lambda. So here, grid search works on the principle that we are going to still have the same type of regressor. So I'm just copy and paste it here. And in addition to that, so I have 10 cross-validation iterations that I can do. But in addition to that, I'm going to change the value of alpha. So it can be 0, it can be 100. It's up to me to decide. And this is an information that is going to be stored in the grid values to be tested. So in this case, for example, I'm going to write params equals, and I'm just going to copy paste some values that I have over here so that you see actually params in this case can take one attribute, but it can take many more than that. So we are going to multiply by 10 the score by the number of values. So we are going to apply 10 iterations with alpha equals 0, with alpha 10 iterations more with alpha 0.05, etc., so on and so forth. So we are going to have even a bigger possibility to maybe find the best parameters that we can have. So here what I can do right now is to put all this information and all these parameters in the function grid search cv. So grid search equals grid search. This is how it is spelled actually. So this is the regressor. So I'm going to add the regressor over here, and I'm going to this regressor to add the parameters and the cross-validation CV equals 10. So once again, CV being the number of folds to be used for cross-validation. And so now actually what I can do is to fit all this into the X train and Y train, just as we did with cross-validation. So here I'm going to just say grid search for dot fit X train, Y train. And so now, while performing this, I would expect to have better values. I would expect to actually come up with even a better score than the one that I previously had, just because before, by default, the reach has a particular lambda. Now I was able to change this particular lambda and maybe add some variety in my example. And so what can I do right now? Well, actually, I can search what the best parameter out of all these ones that were implemented here was. So in order to do that, I'm just going to write grid search dot best underscore params. So alpha 0.5 is a good one. Maybe I would also try 0.7 the next iteration. And also I would be interested to see what the grid search best score is. So did we succeed in beating this particular score? I'm not sure about what the alpha default value was of reach regression, but I can search this right now. So I'm searching for reach, and yeah, indeed, alpha of 1 is the default value for the attribute alpha or lambda in this case. And so my grid search says that a better attribute might be maybe 0.5. Let's actually see. So here I'm going to see the score. Did we succeed in beating the value or not? So actually it is not such a big difference, and apparently we didn't do such a good job. So it's just to show you actually that by trial and error you can achieve great things, or if you don't achieve great things, well, you just need to keep pushing the limits and moving on. Okay, so now we were talking about this for the X train and Y train, so we didn't do like the best performance ever, but it's just for a demo purpose. And so now we can just score this on X train, Y train. So let's do just that score, X underscore train and Y underscore train. Yeah, so let's do that. So this is the value for the train for my score, and I'm going to do the same thing for my test. Let's see for my test if the values are better or not. Okay, so for the test, apparently they are a bit better, but the values for test and train are pretty similar, which indicates that there is not a lot of discrepancy in the variety of the values that we have in the two data sets, train and test, which is nice. Maybe we would like to incorporate even more information, even more observations. Maybe we would like to add higher variety of features and to modify them a bit more. We could also implement other machine learning algorithms. Maybe the regression, in this case the linear and rich regression, are not very good, so let's keep on trying to test some other options. That's why AI platforms are great, because this capacity of having grid search integrated in order to tune your hyperparameters is a great thing to have. That it's pretty bothersome when doing it manually, but which is a pretty cool one when you are able to just use the platform's functionalities. So that was a bit the idea behind this. Of course, all these points need to be treated in more details in case you are interested in doing that, maybe the next time. So thank you for listening. I hope that you grasped the idea of cross-validation and grid source CV for tuning your hyperparameters, and looking forward to any feedback with respect to this. Have a great end of the day. Cheers.